So welcome back, guys. Right, we're still on Chapter 9, Spanning Tree Protocol Concepts. Again, taking it slow, we're taking our time. Sunday, hopefully, if we get through as much as I want to get through, we'll go ahead and touch on having a lab, right? Because I really want to do that, but I really want to make sure I touch on theory so we don't miss anything. So let's see how much we can get through now in the next 15 to 20 minutes. I'm gonna try to keep it short. Um, but last time we were talking about, we spoke on the election process of a root bridge or the root switch within a redundant topology. Okay, we went through that election process. We worked through that, right? It makes sense on what's the election process looks like electing a root bridge. First, the switches are going to look at the switch that has the lowest priority within the BPDU, right? Those BPDUs are sent frequently, right? We haven't gone through timers, right? But those BPDUs are sent frequently to switches, right? As soon as we got a connection, those BPDUs are exchanged or received. That said switch is going to look at the received BPDU and say, hey, does these values, are they lower than my current values, right? Because lower is better, right? So if the lowest one, right? If the lowest BPDU has the lowest priority, excellent. That's going to become the root switch or the root bridge. Okay. If there is a tie, right? The priority, was set as a default priority. Then the tiebreaker is going to be the switch with the lowest MAC address. The switch with the lowest MAC address will be chosen as the root bridge within a redundant topology. Okay. Now that we've spoken about that, we need to speak about something else within the topology. We have our root bridge, right? Now, in terms of spanning tree, we have to discuss the other switches, right? And the other switches need to choose which port will be the root port. Okay, right? This is the second part of the process. So the second part of the spanning tree process occurs when each non-root switch chooses its only, right? Its only root port. So there's always only one root port on a switch, on a non-root switch. Okay. A switch's root port interface, right, has at the least cost. Okay, we're gonna go over that in a second. Has the least cost to reach the root. Okay. All right. So if we're looking at this diagram, right, we're looking at figure 9-5, right? We see, right, we have the same three switches, right? We don't have no visibility on priority, what have you, right? But we see, right, switch one has already won the election, right? It's already become the root switch. Now we have to consider the cost, right? So switch three, right? Let's take a look at switch three. Switch three has two possible physical paths to get to the root, right? We have gigabit 0/1 that has a cost of 5, and we have gigabit 0/2, which is a cost of 4, right? We'll focus on this first, right? It has a link cost of 4, okay? But then it also has to go through switch 2. That link cost is a cost of 4. So 4 plus 4 equals what? 8, right? So we have a total cost of 8. So from switch three's perspective, it's going to choose the link with the lowest cost to be the root port. That port is going to be gigabit 0/1. Okay. This is how a human, right? Because I want you guys to be able to do this on a piece of paper without a lab doing it for you or software doing it for you. Because if you can architecture this, right, and calculate this on paper, you guys will be able to pass your exam. Okay. All right. So this is how it would look if you guys were to do this on a piece of paper, right, and calculate the root port. All right. So, right, typically, right, what we just went through, the switches do the same thing, right? But it's a slightly different process, right? Um, First things first, right? Um, what's going to happen is the switch is going to go ahead and add their local interface costs to the root costs, right? Listed in each received hello BPDU, right? Then right? The port cost, right? The port cost is always going to be a decimal value, okay? And that's going to be assigned to the interface, right? Per VLAN, by the way. Let me make sure I say that. And we haven't got to the nitty gritty yet, but per VLAN, there will be a cost to each interface, right? What this is for the purpose of providing an objective measurement that allows spanning tree to choose which interfaces to add to the spanning tree topology. Okay. The switches also look at the neighbor's root cause, right? And it's also going to go ahead and announce that, right, in the BPDUs that they send off to neighbor switches. Okay. So let's take a look of how, right, of how switches actually do that, right? How each switch's control plane does the calculation process. Okay. So let's go ahead and look at this for a second, right? Let's focus on this process, right? The root switch, let me go ahead and get my pencil, by the way. The root switch sends hellos, right? It's sending constant hellos, right? With a listed root cost of 0. Makibe, why do you think the root is sending a cost of 0? A root cost of 0. Good talk.
Because the root cost is zero. What do you mean?
So if we're looking at switch one, it's sending out, if we're looking at this diagram, right? It's sending out hellos with a root cost of 0. Why would it be sending out hellos with a root cost of 0?
Because it's the root switch.
Exactly.
Okay.
Exactly. The idea is that it's the root switch, right? But the hello BPDU is not going to change no matter if it's the root switch. So, right, what they implemented in this technology is said, hey, from the root switch, you're just going to send a cost of 0. Excellent. You're the root. Okay. So let's go ahead and look at switch three, right? Let's break this down, right? If we're looking at switch three, right, and we're taking into account this hello from switch one with the root cost of 0. Okay. Okay. And then what's going to happen, right, is switch three has its interface has a cost of 5. Okay. So now let's do the math. 0, right? Root cost, right, that we receive from the BPDU, plus the interface cost, plus 5 equals 5. So the cost to go ahead becomes 5, right, for port gigabit 0/1. Okay. Going to the right, right, if we're looking at gigabit 0/2, we have something a little bit different, right? So if we go all the way up to switch one, it does the same thing that it did to switch three. It's sending out BPDUs with a root cost of 0. Okay. The interface cost for gigabit 0/2 on switch 2 is 4, right? In that calculation, it's calculating the received BPDU's root cost. Okay, that's the first number. So the received hello BPDU root cost, right? That value plus its own interface cost to find out, right? The cost, right, to reach the root, right? This link's cost. The cost is 4. Okay. All right. So, and we'll talk about switch two's root port in a second. But we have that cost there. We have that value there. That's how we got there. Okay. Let's do the same thing for switch three's gigabit 0/2. So switch two is going to do the same thing. It's going to send its hello BPDU. Within the hello BPDU, we have, right, what the root cost is for switch two. It's did its calculation and it says, hey, that value is 4. So I'm going to go ahead and put 4, right, to start my calculation, right? But now I need to find out what my interface cost is. My interface cost is a 4. So now I'm going to do 4 plus 4. equals 8. Now I need to go ahead and compare ports. Okay. So I determined, right, if I'm switch 3, I determined the root cost out of gigabit 0/1 is 5. And the root cost out of gigabit 0/2 is 8. Okay. I'm going to go ahead and select gigabit 0/1 has the root port, right? Because the cost to reach the root switch through that port, right, has a lower cost, which is 5, than the alternative gigabit 0/2 with the cost of 8, right? Right? Let's go to switch. Let's go ahead and go to switch 2. Let's do the reverse, right? Gigabit 0/2, right? It has a cost of 4, right? To reach the root. Okay. To reach the root through gigabit 0/1 on switch 2, what do I have to do? I have to add 4 plus what? 4 plus 5. So 9 is better than 4. This is going to be my root port. Okay. Okay. So with all this being said, right, and we talked about, you know, selecting the root port with each election process and the future election processes of different technologies that you guys will learn about in the future within your CCNA, we always need a tiebreaker in case the election has the same values, right? Right? Similar to this, right? The switches need some type of way to have a tiebreaker in case the best root cost is tied for 2 or more paths, right? If a tie occurs, the switch applies these 3 tiebreakers to the paths that tie in order as follows. 1, choose based on the lowest neighbor bridge ID. Okay. 2, choose based on the lowest neighbor port priority. And 3, choose based on the lowest neighbor internal port number. And again, they go over that on page 234 in your book, but I'm going to send you an additional video that goes over this, and I'm going to make sure we cover this in our lab. Okay. So let's keep this. I want to go ahead and keep this diagram, right? Because there's some things we need to touch on before we have a lab. Okay. So we have here, we have the root, right? So this is a designated port. This is a designated port, right? And what you guys learned, if it's a designated port, it's in a forwarding state. You guys also learned a root switch, all of its ports, right, are going to be in a forwarding state. Okay. We have our root port. We identify what our root port was. Okay. We identify what our root port was. Okay. That root port, because we need to communicate with the root, right, from a logical standpoint, that's also always going to be in a forwarding state. Okay. What else do we have to take care of? We have to take care of the link between our non-root switches, right? Because this is the basis of spanning tree is having redundant links. Okay. Right. So we need to take care of this side of the house. Okay. So let's do that. Right. So the final step in spanning tree, right, um, is choosing the designated port, right, on the non-root switch segment, right? Non-root switch to non-root switch segment, right? The switch with the lowest root cost wins the competition. Simple as that, right? With 2 switches on the end of the link, the switch with the lowest cost to reach the root becomes the designated switch. Okay. With its port on that link becoming the designated port on that segment, right? On a link with a switch in the second device that does not use spanning tree, right? The switch becomes the designated port. Okay. I know that was a lot, so I'm going to make it easy for you, but I want to read off this theory so it makes sense, right? The process to choose the designated port begins with the switches forwarding hellos onto the link. The hello messages include a field to list the root cost, right, of the switch that forwarded the hello, right? Determining which switch with the lowest root cost requires a simple comparison. Once a switch port becomes a designated port, it continues to forward hellos on that link, right? So let's do this. Let's go to a better drawing. Oops, there we go. Let's go to 9.4. Okay. So let's talk about in 9.4, right? So in 9.4, right, we're looking at what I want to do with this. Yeah. So we're looking here, right? And we're seeing the hello messages here. Okay. And we're seeing hello messages from switch 2 to switch 3, right? And this is where it's determining, right, the designated port for this segment, right? Right? And we see switch 2, switch 3, listen their root costs. I have a root cost of root 4, a root cost of 4. I have a root cost of 5, right? Right? So since switch 2 has a lower cost, right? Switch 2, right, gigabit 0/1, right, becomes the designated port for that link, okay? Because it has a lower root cost between the switches, right? That designated port gets into a forwarding state, okay? Now, what's going to happen? What's going to happen to gigabit 0/2? DeMarco, do you know?
You said what's gonna happen with which can you repeat that? My bad.
Sure,
I
sure.
was I was paying attention. My son right here too though.
It's okay. It's all right. So we have our root switch. Let me
Uh-huh.
add this drawing, right? We have our root switch. We have our we have our designated ports, right? Because we're building the switches are building out their spanning tree topology. We already chose our root ports, right? So if we did all of that, what do we have left to do? We have to choose our designated switch on our non-root switch segment, right? This is the segment, by the way. And we need to choose which one is the better switch to become the designated switch. Well, the election of the designated switch happens with both of the switches sending hellos to each other. And for the switch that has the lowest root cost, right? Because that's a value that's within that frame, that BPDU frame, the hello. Whoever has the lowest cost wins the election and becomes the designated switch. Switch 2 has the lowest cost of 4, right? So now that port on gigabit 0/1 is going to become a designated port. It's going to be in forwarding, and the switch is going to become a designated switch. Okay, it's no longer a non-root switch within the topology. It is a designated switch, which leaves us with switch 3. Okay,
Uh-huh.
with that being said, right, and we're talking about spanning tree, what happens to gigabit 0/2 on switch 3?
So gigabit/2 on switch 3, that will become a because it got a root cost of 5. Would that become a I want to say would it become a blocking port or
Absolutely.
all right, got you.
This will become a blocking port. Okay, right? The rule of thumb for spanning tree is we need one path outside of the topology, right? Because if we have multiple paths, that's when we have a broadcast storm. Okay, this is what spanning tree came to fix, right? But let's talk about designated switch and the designated port for a second, right? Let's go back to the election process for designated switch, right? If for some reason, right, switches on the non-root segment are sending those hello BPDs, right? And guess what? We have a tie, right? The root cause for switch 3 is a 4 and switch 2 is a 4, right? The switches break that tie by choosing the switch with the lower bridge ID, right? And you guys know what's in the bridge ID. It is the priority number, right? And the MAC address, okay? So first, it's going to look at the priority. If priority is the same, it's going to choose the switch with the lowest MAC address. So with that being said, when you guys are configuring, you guys are managing your networks. If you guys want to be in charge of how your topology works, make sure you configure your priority so you can manage and control how your spanning tree topology is architecture. Okay. If not, you may put in an old switch, right, that has a lower MAC address, but and you put in a newer switch that has a newer MAC address, right? Your idea in your mind in regards to architecture is that this newer switch is going to be, right, maybe the designated switch. That's what you want. But since you did configure the priority to make that happen, right, it's going to go through that tiebreaker process. And of course, that older switch, since that's a lower MAC address, is going to win that tiebreaker, right, of bridge ID, okay, to become a designated switch. So just remember that, okay? You guys will need to know this, right, and know this concept. So please reread chapter 9, the section talking about some of the foundational topics in spanning tree basics, okay? Um, and influencing the spanning tree topology, okay? Um, let's go ahead and erase this. Okay. All right. We talked about the tiebreakers, stuff like that. We talked about that. One other thing, right? We do need to talk about is two additional tiebreakers are needed in some cases. Although these would be unlikely, right? A single switch can connect to two or more interfaces on the same collision domain. Okay. By connecting to a hub, in that case, this one switch hears its own BPDUs. So if a switch ties with itself, two additional tiebreakers are used. The lowest interface, right, spanning tree, right, priority, and if that ties, the lowest internal interface number. Okay, all right. So hopefully that makes sense. Please take a screenshot of this, right? We talked about the diagram, so we don't really need to go over that. It's basically explaining how we converged the topology, of course, because what you guys saw was spanning tree convergence, right? We saw the election of the root bridge, we saw the election of the root port, we saw the election of the designated switch, okay? All right, and we saw the election of the blocking port. Okay, what you guys saw, right, was spanning tree convergence, and our switches do it right in milliseconds. Right, it took us a while to go ahead and write that down and do it, but it took milliseconds to go ahead and do right on the switches. Right, that's why it has the most expensive chips and all that stuff. Okay. With that being said, I'm going to end here. And then Sunday we're going to have a lab on this. Okay. All right, we're going to do a little bit of theory, but I want to touch on link costs and what have you. Okay.
Gotcha.
All right, guys.
All
All right,
right, sounds
appreciate it,
Thanks.
Dave.
good.
No
Thanks,
problem.
Dave. Bye.
Bye. Bye.